Good afternoon. My name is Rinku Dewri. I am with University of Denver, and this work was done in collaboration with Toan Ong, who is at the Anschutz Medical Campus associated with the University of Colorado Denver, and my colleague Ramakrishna Thurimela. Okay, and I'm going to talk about linking health records. So I'm going to dive into the problem as to what does it mean to link, let's say, databases in general. Okay, so in our case, a database, it has a kind of like a table form which has records. Each record could be about one individual, and then you have fields or attributes. And the application scenario we were looking at was these records were health records. Okay, so attributes could be different related to the medical condition of a certain individual, and part of the attributes would be demographic data, name and identifiers like social security numbers or address, and so on and so forth. So we have now two parties having two such databases, or two such health databases, and they're distributed in nature. So they are at different locations, and often that the case is that they do not want to disclose the database, again due to the sensitive nature of the data contained in the databases. Okay, so the idea behind linking is to then somehow figure out if records in one database and records in another database belong to the same individual. Okay, so you could have overlap in the databases. If, for instance, in a regional setting, there are multiple health providers and people often switch jobs moving from one health provider to another, and so on and so forth. So there could be multiple instances of a same person's record that will exist. Now the reason we want to do this is because we want to facilitate what is called federated queries. So you have a query on a health database. Okay, give me the number of people with a certain glucose level, with a certain heart condition. Okay. First of all, both databases could contain information, in which case we want to assimilate the information, collate it, and remove inaccuracies that can appear because of overlap. Second, maybe part of the data is in database A, part of the data is in database B. So federated queries will allow us to do queries across attributes that appear in different databases. Okay? So that's the whole idea behind creating such kind of a platform. And in Colorado, Anschutz Medical Campus, they were working with this framework called Safety Net, which basically tries to achieve things like this. Okay, okay, so we will take this particular problem description of databases linking and then see how it can be done. And the greedy matching way to do it would be to take a record in A and compare it with every record in B, and by comparing I mean come up with some kind of a score. Okay, how what's the some kind of a number that says, okay, this record in A and this record in B actually belong to the same person. Okay, and that score itself is computed using some weighted sum of scores computed on the attributes themselves. So if you're talking about one record in A and another record in B, you will also have the method to compute the similarity between an attribute in the records. For example, how to compare the name here and the name in another record, okay, in B. So then the question is, okay, we want to compute, that means scores for two strings. Okay, how similar two strings are. That's where it boils down to. Okay. Now, what are the problems? There are different methods to do that. So one is we have to take account of errors in the data, because when data is input into the databases, there will be errors. So all of these represent the same person, and so in the first case, you missed the letter. Here's some transposition that happened. First name, last name has been swapped, and key slip, okay, M and M. So but both of them in all of these names are about the same person. So the technique that is commonly used is to do bigram matching. So what you do is you break the string into bigrams of every two subsequent characters, and then do that on both sides. you get a set of bigrams on both sides, and then you have some measure to figure out, okay, what is the similarity between the two sets. Okay? And one way to do that would be something called Dye's coefficient, which looks at the intersection between the size of the intersection between the two sets, and there's a formula involved. Okay? You can compute different other scores also. So then what it means is the whole thing then boils down to finding out the intersection size of the two sets. Okay? Which means that we need to be able to figure out if two elements are equal or not. Okay? If two elements are equal from two different sets, they are in the intersection. Okay, so it doesn't look so bad, but then the problem arises because now we are saying that, okay, we cannot see the strings. Because again, if you remember, they're in different databases and their privacy, the providers are not willing to reveal the databases as such, so we cannot look at the strings. Okay? So one way to handle that would be use some kind of hashing, a cryptographic hashing in this case. So let's say the two sides, they come up with keys k and k prime. Of course, these are strings, so they have to be mapped to some kind of a number. So in this case, we actually map it to primitive roots, and we do some kind of a modular exponentiation. Okay? So each party does that on their side, and then sends the result to the other side, who then just takes the result and applies its key. Again, does a modular exponentiation using its own key. Both parties does the same thing, and then sends these, whatever these values are, to some kind of a linkage agent. Okay? And then the agent is going to look at the two values and say, okay, these are equal. Okay, fine. That means the values that both parties had, or the bigram that they had, was equal, otherwise not. So that way, you basically doing a check for equality, and you can do the intersection, and then you can compute the attribute score, and then compute the record score. Okay. Now, if I am to do this, implement this, and exactly on a large database, then if I have, let's say, 100,000 records in each database, each site, then this could take years to compute because of the modular exponentiation. There are some numbers, estimates given in the paper. You can look at it. And it would result in the transfer of tremendous or a huge amount of data in petabytes. Okay? But you think about it, each string will be broken down into bigrams, and this operation being shown is for every bigram comparison. And if you're doing a quadratic comparison, then again, it's basically just scales up. Now, there are other methods also, methods based on what the medical community has been using. It's called Bloom filters, where you encode the same thing in Bloom filters. But on and off, Bloom filters have been attacked, shown to have weaknesses. So there is the platform, the landscape is not, we have not figured out what's the best there. Okay? Here, this approach has mostly been not used because of all this high computation and high communication cost problem. So we want to see what we can do in this part. So the first thing we do is we say, okay, let's not have both sides pick these keys every time you have to compare bigrams. Okay? Let's just decide on a fixed set of keys and then pick keys from that particular set, because what that gives us then is the ability to pre-compute all these different exponentiations. Okay? And pre-computation can be done because if you think about a set of bigrams, it's not really that large, maybe 4,700 something. So that's what we do. We take all the possible bigrams, okay, and then we do a permutation. So this is what every party does. It does a permutation of this set. So no one knows what is here except for the party, and then applies or does a pre-computation, which is basically doing a modular exponentiation on every bigram in the permuted set. Okay? And then just combines this all together and sends it to the other side, okay, side B. Similarly, this particular side is also going to receive something from the side B. Okay? It's level 1 output. Now, the time it takes to do level 1 output, if I am using 50 keys, 2048-bit primes, the 8 got away. So 8 threads, then this is going to take roughly 3 minutes to do, and it produces an output of 58 megabytes. Okay. So next is we take the data from the other side, okay, and then we apply the same process. So we apply the keys, do the modular exponentiations, and then we get the second level precomputation, which is sent to the linkage agent. Okay. And to do this in the same setting, it's going to take around 2.2 hours, and the output is around 68 megabytes. Of course, this is after we do some truncation. Okay. You don't have to keep the entire 256 bytes of the output. You can keep just enough so that every entry is unique in there, which in our case, in this case, was 6 bytes. Okay. Now, this is what the output looks like from the different parties at the linkage site. So you have these different values. So every site can now just refer to a bigram using an index, okay, and it is a permuted index because it knows the permutation function, it knows which index to refer to, and then it can choose a key. Okay, so you can use that, the linkage agent can use that to look up the values in these two tables, one received from A, one received from B, and then they do a quick check on the values. So this is how the linkage is going to happen at the linkage agent side. So using this process, we were able to compare 100,000 records in each pair. That's around 10 billion record comparisons. And it had two attributes, names and addresses. It took around 80 minutes to do that. Okay. Now, the problem with this method is with frequency attack. So if we know that there is a certain distribution of bigrams in, let's say, in names, if we uniformly pick keys for use in that method, then each key will also display the same kind of distribution. Okay? So there is it's susceptible to a frequency attack in that case. So then what we say is, okay, let's not pick keys uniformly at random, let's use some kind of a smoothing. So for bigrams that appear more number of times, let's use more keys. For bigrams that appear less number of times, appear less keys. Okay? As a result of which, what happens is that the keys start to show a distribution very close to being uniform. Okay? Now, of course, there is some residual risk, and then in the paper we show how we compute it, and there is some results. Okay? Now, there is advantage to have using a single key per site. Okay? First of all, if I just use one key, then my pre-computation data will be very small, so small that it can fit in the cache. In the cache, if it can fit in the cache, then the lookups will be much, much faster when I do this linkage operation, because the linkage is nothing but lookups on the table. Okay. Second, I can use a linear time algorithm to do the set intersection using a hash table or something. Okay. But of course, the frequency attacks are still possible, and I do not have keys now to choose from to flatten the frequencies. So one way to handle this would be insert dummy records into the actual records. Okay? So if you look at the distribution of the frequencies in some attribute in the bigrams, then this is the uniform distribution. If all frequencies were at this level, it would have been uniform. So we could use this empty space, basically, which tells us how many the count of bigrams we can use for each of these to create dummy records. But if we do that, then we are going to have much more number of dummy records than actual records. Okay? So the technique we use is to do smoothing in a cluster. So we look at the distribution, let's say we divide it into 5 clusters, and then we do smoothing in each cluster. Okay? As a result of which, the frequencies now become something like this. So they are uniform within the same cluster. Okay? Again, if we do a single key now, that 80 minutes could become 10 minutes for records, 100,000 records at each site. Okay. So if you look at the exposure risk now, there will always be some bigrams that have higher exposure risk than in others. Single key usually it is faster, but it has a slightly more residual risk than in the multi-key approach. Okay. But note that knowing one or two few bigrams is not sufficient to infer the whole string. You need to know a significant number of them for you to be able to build a string back. Okay. And then if you're worried about, okay, what's the precision leak call? Again, this is about a greedy matching algorithm. We didn't explore anything outside of that. The precision and recall, that is the ability to match the records, were pretty good, close to 98% in both cases. Okay. Again, there is more in the paper about the whole processing architecture, how do we generate data sets, our implementation, how do we compute the exposure, all of that you can find in the paper. Okay. So I believe we have provided some hint on how to implement this linkage algorithm that can use cryptographic methods and have a feasible runtime on linking large-scale databases. Yeah. And then in the next step, we probably want to move towards something like internet scale linking, which will be much, much bigger in scale. Okay, thank you.